In set theory, an ordinal number, or ordinal, is one generalization of the concept of a natural number that is used to describe a way to arrange a collection of objects in order, one after another. Any finite collection of objects can be put in order just by labeling the objects with distinct whole numbers. Ordinal numbers are thus the labels needed to arrange infinite collections of objects in order. Ordinals are distinct from cardinal numbers, which are useful for saying how many objects are in a collection. Although the distinction between ordinals and cardinals is not always apparent in finite sets, different infinite ordinals can describe the same cardinal. Ordinals were introduced by Georg Cantor in 1883 to accommodate infinite sequences and to classify derived sets, which he had previously introduced in 1872 while studying the uniqueness of trigonometric series. Like other kinds of numbers, ordinals can be added, multiplied, and exponentiated. The finite ordinals are the natural numbers 0, 1, 2, since any two total orderings of a finite set are order isomorphic. The least infinite ordinal is omega, which is identified with the cardinal number. However, in the transfinite case, beyond omega, ordinals draw a finer distinction than cardinals on account of their order information. Whereas there is only one countably infinite cardinal, namely itself, there are uncountably many countably infinite ordinals, namely omega, omega plus 1, omega plus 2. Omega 2, omega 2 plus 1, omega 2, omega 3, omega omega, omega omega omega, epsilon 0. Here addition and multiplication are not commutative. In particular 1 plus omega is omega rather than omega plus 1, and likewise, 2 omega is omega rather than omega 2. The set of all countable ordinals constitutes the first uncountable ordinal omega 1, which is identified with the cardinal. Well-ordered cardinals are identified with their initial ordinals, i.e., the smallest ordinal of that cardinality. The cardinality of an ordinal defines a many-to-one association from ordinals to cardinals. In general, each ordinal alpha is the order type of the set of ordinals strictly less than the ordinal alpha itself. This property permits every ordinal to be represented as the set of all ordinals less than it. Ordinals may be categorized as 0, successor ordinals, and limit ordinals. Given a class of ordinals, one can identify the alpha-th member of that class, i.e., one can index them. Larger and larger ordinals can be defined, but they become more and more difficult to describe. Ordinals extend the natural numbers. A natural number can be used for two purposes: to describe the size of a set, or to describe the position of an element in a sequence. When restricted to finite sets, these two concepts coincide. There is only one way to put a finite set into a linear sequence, up to isomorphism. When dealing with infinite sets, one has to distinguish between the notion of size, which leads to cardinal numbers, and the notion of position, which is generalized by the ordinal numbers described here. This is because while any set has only one size, there are many non-isomorphic well-orderings of any infinite set, as explained below, whereas the notion of cardinal number is associated with a set with no particular structure on it. The ordinals are intimately linked with the special kind of sets that are called well-ordered. A well-ordered set is a totally ordered set in which there is no infinite decreasing sequence. Equivalently, every non-empty subset of the set has a least element. Ordinals may be used to label the elements of any given well-ordered set and to measure the length of the whole set by the least ordinal, that is, not a label for an element of the set. This length is called the order type of the set. Any ordinal is defined by the set of ordinals that precede it. In fact, the most common definition of ordinals identifies each ordinal as the set of ordinals that precede it. For example, the ordinal 42 is the order type of the ordinals less than it, i.e., the ordinals from 0 to 41, and it is generally identified as the set 0, 1, 2, 41. Conversely, any set of ordinals that is downward closed, meaning that for any ordinal alpha in S and any ordinal beta less than alpha, beta is also in S, is an ordinal. There are infinite ordinals as well. Perhaps a clearer intuition of ordinals can be formed by examining a first few of them. As mentioned above, they start with the natural numbers 0, 1, 2, 3, 4, 5. After all natural numbers comes the first infinite ordinal, omega, and after that come omega plus 1, omega plus 2, omega plus 3, and so on. After all of these come omega 2, omega 2 plus 1, omega 2 plus 2, and so on, then omega 3, and then later on omega 4. Now the set of ordinals formed in this way must itself have an ordinal associated with it, and that is omega 2. Further on, there will be omega 3, then omega 4, and so on, and omega, then omega squared, and much later on epsilon 0. This can be continued indefinitely far. The smallest uncountable ordinal is the set of all countable ordinals, expressed as omega 1. Definitions. Well-ordered sets. In a well-ordered set, every non-empty subset contains a distinct smallest element. Given the axiom of dependent choice, this is equivalent to just saying that the set is totally ordered, and there is no infinite decreasing sequence. Something perhaps easier to visualize. In practice, the importance of well-ordering is justified by the possibility of applying transfinite induction, which says, essentially, that any property that passes on from the predecessors of an element to that element itself must be true of all elements. If the states of a computation can be well ordered in such a way that each step is followed by a lower step, then the computation will terminate. It is inappropriate to distinguish between two well-ordered sets if they only differ in the labeling of their elements, or more formally, if the elements of the first set can be paired off with the elements of the second set such that if one element is smaller than another in the first set, then the partner of the first element is smaller than the partner of the second element in the second set, and vice versa. Such a one-to-one correspondence is called an order isomorphism, and the two well-ordered sets are said to be order isomorphic, or similar, provided there exists an order isomorphism between two well-ordered sets. The order isomorphism is unique. This is exactly what the ordinals provide, and it also provides a canonical labeling of the elements of any well-ordered set. Formally, if a partial order less than is defined on set S, and a partial order less than is defined on set S, then the poses are order isomorphic if there is a bijection F that preserves the ordering. That is, F less than F if and only if A less than B. Every well-ordered set is order isomorphic to the set of ordinals less than one specific ordinal number, the order type of under their natural ordering. Essentially, an ordinal is intended to be defined as an isomorphism class of well-ordered sets. That is, as an equivalence class for the equivalence relation of being order isomorphic. There is a technical difficulty involved, however, in the fact that the equivalence class is too large to be a set in the usual Zermelo-Fraenkel formalization of set theory. But this is not a serious difficulty. The ordinal can be said to be the order type of any set in the class. Definition of an ordinal as an equivalence class. The original definition of ordinal number, found for example in Principia Mathematica, defines the order type of a well-ordering as the set of all well-orderings similar to that well-ordering. In other words, an ordinal number is genuinely an equivalence class of well-ordered sets. This definition must be abandoned in ZF and related systems of axiomatic set theory because these equivalence classes are too large to form a set. However, this definition still can be used in type theory and in Quine's axiomatic set theory, New Foundations and Related Systems. Von Neumann definition of ordinals. Rather than defining an ordinal as an equivalence class of well-ordered sets, it will be defined as a particular well-ordered set that represents the class. Thus, an ordinal number will be a well-ordered set, and every well-ordered set will be order isomorphic to exactly one ordinal number. The standard definition, suggested by John von Neumann, is: each ordinal is the well-ordered set of all smaller ordinals. In symbols, lambda equals 0, lambda. Formally, a set S is an ordinal if and only if S is strictly well-ordered with respect to set membership and every element of S is also a subset of S. Note that the natural numbers are ordinals by this definition. For instance, 2 is an element of 4 equals 0, 1, 2, 3, and 2 is equal to 0, 1, and so it is a subset of 0, 1, 2, 3. It can be shown by transfinite induction that every well-ordered set is order isomorphic to exactly one of these ordinals, that is, there is an order-preserving bijective function between them. Furthermore, the elements of every ordinal are ordinals themselves. Given two ordinals S and T, S is an element of T if and only if S is a proper subset of T. Moreover, either S is an element of T, or T is an element of S, or they are equal. So every set of ordinals is totally ordered. Further, every set of ordinals is well-ordered. This generalizes the fact that every set of natural numbers is well-ordered. Consequently, every ordinal S is a set having as elements precisely the ordinals smaller than S. For example, every set of ordinals has a supremum, the ordinal obtained by taking the union of all the ordinals in the set. This union exists regardless of the set's size, by the axiom of union. The class of all ordinals is not a set. If it were a set, one could show that it was an ordinal and thus a member of itself, which would contradict its strict ordering by membership. This is the Borel-Leiforter paradox. The class of all ordinals is variously called ordon, or infinity. An ordinal is finite if and only if the opposite order is also well-ordered, which is the case if and only if each of its subsets has a maximum. Other definitions: there are other modern formulations of the definition of ordinal. For example, assuming the axiom of regularity, the following are equivalent for a set X. X is an ordinal. X is a transitive set, and set membership is trichotomous on X. X is a transitive set totally ordered by set inclusion. X is a transitive set of transitive sets. These definitions cannot be used in non-well-founded set theories. In set theories with Uri-elements, one has to further make sure that the definition excludes Uri-elements from appearing in ordinals. Transfinite sequence. If alpha is a limit ordinal and X is a set, an alpha-index sequence of elements of X is a function from alpha to X. This concept, a transfinite sequence or ordinal index sequence, is a generalization of the concept of a sequence. An ordinary sequence corresponds to the case alpha equals omega.